next we have a presentation from S Liu from Carnegie Institution right here, and she will tell us about the origin of the negative longitudinal piezoelectric effect. There you go.
Great. Thank Ilya for the introduction, and also thank the organizer for the invitation. So in today's presentation, I will introduce and explain this negative longitudinal piezoelectric effect, which was considered as a real anomaly and didn't get that much attention. So in this talk, I will show you with both quantum mechanics calculations and material informatic methods that this is actually a quite common phenomena, and this work was carried out here at Carnegie, collaborated with Ron, and with funding support from Office Naval Research, Carnegie European Research Council, and computational supports provided through HPC MO. During my presentation, I will jump to a slightly different topic, but it's also highly relevant to this workshop. So for this audience, I probably don't need to speak too much about the importance of piezoelectric materials, which is truly a class of smart materials that can convert mechanical energy to electrical energy and vice versa, making them very useful in a lot of modern devices from sonar to MEMS nanogenerators and vibrational energy harvester. So the piezoelectricity is characterized by the piezoelectric coefficients. In this presentation, I will mainly focus on the longitudinal response, which is the response along the polar axis. There are two piezoelectric coefficients. One is E33, which relates the change in polarization to the change in strain. Another one is D33, which reflects the strain change in response to external electric field. And these two piezoelectric coefficients are related to each other through elastic compliance. Developing better piezoelectrics with larger D33 and E33 is active, ongoing research area, and there are a lot of good reasons for that. We sort of take it for granted that E33 and D33 are positive because for all the materials we care about or we have been studied have positive D33, but these two piezoelectric coefficients can be negative, and this is called a negative longitudinal piezoelectric effect. And this is a very counterintuitive phenomena because based on the definition, when we stretch the material, increasing the strain, the polarization actually becomes smaller. So equivalently, when we turn on electric field along the polar direction, even though the polarization becomes larger, the lattice constant becomes smaller, giving you a negative D33. So this is very counterintuitive. You may be wondering whether this ever been observed experimentally. Like 2 years ago, it turns out that this negative piezoelectric response was observed in this well-known ferroelectric polymer. So this is the structure for PVDF. The polarization comes from alignment of molecular dipoles, and we can switch this polymer by applying electric field. They measured the polarization electric field hysteresis loop and also the strain electric field hysteresis loop. As you can see here, when the magnitude of the polarization becomes smaller, the corresponding strain becomes larger. When they increase the polarization, the coupling strain becomes smaller. So this is a clear indicator of negative piezoelectric effect. In a paper, they attribute this negative piezoelectric response to the unique microstructures of PVDF polymers with intermixed crystalline phase and amorphous phase. So in other words, it's not intrinsic bark properties. So the question I would like to answer is, are there single-phase bark materials possessing this negative response, and how common are they? I looked into literatures. There were actually scattered reports. I think this paper was from David's group. They look at the piezoelectric coefficients for some 3-5 zinc blende semiconductors. As you can see, quite a few of them have, even though small, have negative E33, in this case along the 111 direction. It turns out Wurtzite boron nitride has pretty decent negative D33 in these two, reported in these two papers. So now the question is, what is the origin of this negative E33, and can we design piezoelectrics computationally? So I will start with the fundamentals of piezoelectricity from quantum mechanics. It is now well established that we can decompose the E33 into two terms. One is this clump ion term that is evaluated by fixing internal atomic coordinates. It reflects it is a purely electronic effect and reflects the change in polarization in response to microscopic strain. And it is very easy to show that if in a classic dipole moment picture, this term is 0, but in real case, we always have charge transfer, so this term is non-zero and is often negative. The second term is called internal strain term. It comes from the atomic relaxations in response to this macroscopic strain change. For most piezoelectric materials we have studied, this internal strain term is very positive and dominates over those negative clump ion terms, so therefore the total E33 are positive. But I think from this table we can see that at this fundamentally there's no physics preventing the realization of negative response, and this equation actually tells us a very general design principle, that is to find piezoelectric materials with small internal strain term. And as you can see, the internal strain term depends on the boron effect charges and also the atomic relaxations. So for piezoelectric materials with rigid potential energy surface, they're more likely to support a negative E33 and D33, and this is our general design principle. That is to find materials with rigid chemical bonds. I looked into literatures. One particular class of ferroelectric materials called hypertension. Again, it's from David's group. I think they talked about this work a couple years ago in this workshop. It is called ABC ferroelectrics. It's a hexagonal crystal, and it is not perovskite. And the nonpolar, you can really consider this nonpolar phase as layer structure with A, B, C stackering. And the polarization comes from the buckling of these BC layers. It caught my attention because in the paper, they also calculated the switching barriers. This figure shows which is essentially energy difference between the polar phase and non-polar phase. So this figure shows the switching barrier and energy difference as a function of polarization for all the ABC ferroelectrics they discovered with first principle high throughput approach. So as you can see, a lot of ABC ferroelectrics are quite rigid. They have very large switching barriers. So particularly for those compounds containing lithium atoms, and lead titanate, I think roughly the switching barriers, the barrier height is around like 0.2 electron volt per formula unit. So clearly, these ABC ferroelectrics are much more rigid than lead titanate. So I think they are very good candidates to start with. But now I'm going to jump to a slightly different topic because these ABC ferroelectrics are, I believe, they're a very robust platform that can enable many novel functional properties. It was proposed that some ABC ferroelectrics are hyperferroelectrics. I think it's a very interesting property that is a proper ferroelectrics with persistent polarization in the presence of depolarization field. So this is the photon spectrum for the nonpolar phase. As you can see, both the TO mode and LO mode are unstable. This is very different from conventional proper ferroelectrics such as lead titanate and barium titanate. We know that only the TO mode is unstable in the nonpolar phase. The consequence of this this unstable LL mode is that hyperferroelectrics can be polar even under ideal open circuit conditions. So in this paper, so I think this figure illustrates the difference. For normal ferroelectrics, this is the polarization as a function of displacement field. As you can see, this line crossed the zero point. So what's happening is when you put a slab of ferroelectric material in vacuum, because of the depolarization field coming from the surface charges, it will kill the ferroelectricity. So under this very ideal open circuit condition, ferroelectric thin film will be, will be non-polar. I think this is now well established. In contrast, for hyperferroelectrics, when you put a slab of hyperferroelectric in vacuum, they can still be polar. And so this really demonstrates the robust ferroelectricity supported by ABC ferroelectrics. I think we decided to look at the charged domain walls in hyperferroelectrics. In yesterday's presentations, we learned that charged domain walls are actually very rare because of this very strong depolarization field. So whenever we have this a pair of head-to-head and tail-to-tail domain walls, we have positive polarization bound charge at head-to-head domain wall and negative polarization bound charge and tail-to-tail domain wall. This creates a huge depolarization field, which will kill the ferroelectricity. And this is indeed the case for conventional ferroelectrics like lead-titanate. So even in a computer, essentially at 0 Kelvin, we can start with a configuration with charged domain walls. But during relaxation, it will spontaneously transform to these single domain configurations because this configuration is not even metal stable. So we carried out first principle density function theory calculations in lithium, beryllium, antimony, and this is a hyperferroelectric. So this is a supercell. It has one head-to-head domain wall in the middle of the supercell and a tail-to-tail domain wall at a boundary. What I show here is the atomic displacements and also the polarization across the supercell. As you can see, it clearly has this well-defined anti-parallel 180-degree charged domain walls. So this really comes from this hyperferroelectricity, the persistent polarization in the presence of very strong depolarization field. So what's surprising is if you look at the polarization in this bark-like region, away from the head-to-head domain wall, you can see the polarization value is very close to the single domain value. So we further look at the electronic structures of charged domain walls. So what's happening is the presence of charged domain walls close the band gap. You may think the system is metallic. Well, you may say it's a polar metal, but what's happening is from the layer resolved density of states, we can see that we have quasi-two-dimensional localized electrons at head-to-head domain wall and also quasi-two-dimensional whole gas localized at tail-to-tail domain wall. So these free carriers almost compensate the polarization bound charge perfectly, therefore screen the depolarization field. We further calculate the electrical conductivity for the single in single domain, also for the supercell with charged domain walls. As expected, along the domain wall, within the plane of the domain wall, the electrical conductivity it has metallic signature, but perpendicular to the domain wall, that is across the supercell, the conductivity is still very low. So we think many hyperferroelectrics, in this case, lithium, beryllium, antimony, are potentially really ideal candidates to study high-density charged domain walls. They may also have potential device applications because of this quasi-two-dimensional electron and whole gas. Okay. So now I'm going back to the piezoelectric properties of ABC ferroelectrics. So we calculate the piezoelectric coefficients with a density functional perturbation theory The protocol is pretty standard. All the calculations are carried out with local density approximation with GBRV superpotential. We use very high energy cutoff, around 60 Rydberg. As you can tell from the table, quite a few ABC ferroelectrics have negative E33 and D33. I just want to highlight two compounds. For these two ferroelectrics, they have very decent E33 and D33. They are comparable with zinc oxide prototypical piezoelectric materials. We also evaluate the piezoelectric coefficients with finite difference method, which I think is probably much more intuitive than density functional perturbation theory. These are the results for lithium beryllium antimony. What I did is to look at the polarization as a function of uniaxial stress and also the polarization as a function of uniaxial strain. With two density functional, they essentially give the same results. The slope tells us the piezoelectric coefficients. So I think this figure is probably more intuitive. So when we stretch the material, that is apply a positive uniaxial strain, the polarization becomes smaller. When we apply a compressive strain with negative strain values, the polarization becomes larger. So it is indeed consistent with the idea of a negative longitudinal piezoelectric response, as I showed earlier. So we also look at the strain change in response to external electric field with finite field method. It's a little bit challenging to get it converged, but at the end we get this nice linear relationship between the strain and the external electric field. As you can see, when we apply the positive electric field along the polar axis, the strain becomes smaller. Again, consistent with the picture of negative piezoelectric response. So we further look at the polarization reversal process in this compound with variable cell largely elastic bound method. So what I show here is the polarization reversal, the switching barrier, while this is the zero field case. So the barrier is high, as we will expect from the very high barrier in the double well potential. And through the switching, all the structure remains to be insulating. And if you look at this intermediate region, when the polarization becomes smaller, the C-axis actually becomes larger. And when the polarization becomes larger, the magnitude of the polarization becomes larger, the C-axis shrinks, contracts. So again, all different methods, all different computational methods are consistent with each other, really demonstrating the presence of negative longitudinal piezoelectric effect. So the origin of this negative response really comes from this negative clamp ion term. So as you can see from the table, for these two compounds, they have negative clamp ion, the same as lactinate, but they have very small, nearly zero internal strain term. However, in lactinate, this internal strain term dominates. So because of this very small internal strain term, these two ABC ferroelectrics have negative E33. We also look at the Boyne free charges and also the atomic relaxation in response to the macroscopic strain. As expected, these ABC ferroelectrics have pretty small Boyne free charges, and it doesn't move that much in response to the external strain. So I think this is very clear to us that the origin of this unusual piezoelectric response relies on the small effective charges and also the rigid potential energy surface. Then the question is how many compounds we can find. The good thing is back in 2015, there's already a first principle based database of piezoelectrics with their E33 calculated with density functional perturbation theory. And these compounds, this is the open source, well-curated data we can access from Material Project. And this database contains nearly 1,000 inorganic compounds. So with just 2 lines, we quickly identify like nearly 100 inorganic crystalline compound with E33 smaller than -1 coulomb per meter square. So this really demonstrates that this phenomena is much common than we thought. Here I just highlight a few examples. So for this is sodium oxide. It's kind of surprising that I look in the literature. This seems to be some kind of high pressure phases. It has a pretty large negative E33 is -9.6 coulomb per meter square. Probably a more detailed quantum mechanical calculations is worthwhile. And this layer structure also has very negative E33, -7.4 coulomb per meter square. And these 2 compounds have already been synthesized. They're non-compounds. They're pretty decent E33 as a negative E33 as well. But as you can see, they're not perovskite structures. So, okay. So a natural consequence of negative piezoelectric response is the pressure-enhanced ferroelectricity. So this gives a very general explanation. So delta P3 is the pressure-induced polarization change. Because now we need to consider the effect from volume change, so we need to use this improper piezoelectric coefficients. So the strain change is negative. For normal ferroelectrics, because of this very positive E33 term, the polarization change is negative. However, for ferroelectric with negative piezoelectric coefficient, this will result in polarization enhancement. And this is indeed what we observed based on our DFT calculations. What I show here is the polarization change as a function of hydrostatic pressure. As you can see, a lot of them, particularly for ABC ferroelectrics with negative E33, they have polarization increasing with increasing hydrostatic pressure. So this makes them very appealing for high-pressure applications. I also would like to put our work in a bigger context. In the literatures, people talk about pressure-enhanced ferroelectricity from time to time. I believe a lot of you are familiar with this work that is lattining. So in this paper, it was suggested or proposed. It was claimed that the ferroelectricity will reappear above some critical pressure. Maybe Ron has some new update, but it's clear that when we apply the hydrostatic pressure, the polarization will become smaller. In this paper, they show that for some improper ferroelectrics, rare earths, ferrite, the polarization will also increase with increasing hydrostatic pressure. But in this case, it is because of zone boundary mode. However, for ABC ferroelectrics, it's a proper ferroelectrics characterized by a zone center mode. So in this paper, they also look at polar instability for some geometric ferroelectrics. Indeed, for some geometric ferroelectrics, so what I calculate is the square of the TO mode frequency as a function of pressure. This is essentially pressure. This is the high pressure region. As you can see, the polar instability indeed get enhanced with increasing pressure. So within this picture, I think ABC ferroelectrics are probably better characterized as geometric ferroelectrics. This the last slide. So it turns out that for some ABC ferroelectrics, the polarization is extremely robust. So what I show here is the polarization as a function of hydrostatic pressure all the way up to 80 gigapascal. And the red line is the polarization. As you can see, it keeps increasing. Around 80 gigapascal, the band gap closes. So it is not because because the structure is metallic, we cannot define the polarization. And this is the band structure. Indeed, at 85 gigapascal, there are some bands across the Fermi level. But what's surprising is even at this very high pressure, 85 gigapascal, the structure remains to be in a polar space group. So we look at a phonon spectrum, and all the phonon branches are stable. So that's why I call this like a high-pressure polar semi-metal. Okay, with this, I would like to conclude my presentation with detailed quantum mechanics calculations, also material informatic methods. We really demonstrate that this negative longitudinal piezoelectric effect is a common phenomenon. We really hope that this work can inspire some more experimental studies. And thank you for your attention. I'm happy to take any questions you have.
All right. Questions?
I have two short questions. First, is there any, do you also see a negative dielectric constant? Second is there any real application for this material?
Negative dielectric constant, we don't see negative dielectric constant. When we turn on electric field, the polarization still becomes larger. The strain becomes smaller. So the dielectric constant is still positive.
So the coupling between dielectric constant and piezoelectric constant, there is a negative sign, right? It's also negative in this case, right? Because your PVDF actually shows a positive dielectric constant, but it has a negative piezo constant. In your PVDF example,
yes,
you showed the hysteresis curve, but your strain curve is kind of abnormal. So that relationship.
The dielectric constant, if my understanding is just the dP over dE, right?
Right.
When you turn on electric field, the polarization still becomes larger. So the dielectric constant is still positive.
What I mean is your dielectric constant usually has a linear correlation with your piezoelectric constant.
Mm-hmm.
History. It's a well-known relationship. So you are suggesting there should be a negative sign. Am I right?
No.
Right.
Right.
Oh, okay.
Okay, good. So the second question is whether there's real experimental, real applications. Well, it's hard to tell. The physics is definitely very interesting, but we thought about what would happen if you put a conventional piezoelectric and material with this negative response, and when we turn on electric field, part of the material want to expand, part of the material want to shrink. That may have some interesting physics at interface or interesting applications. So that's why we really hope that this work can inspire more experimental studies. Yeah.
Okay, thank you.
Compliments for this really nice study.
Thank you.
You had a throwaway remark which puzzled me slightly. You had potassium iodate, and you said it's not perovskite. Now, are you talking about a completely new phase? I mean, the classic potassium iodate is well known. It's not trigonal, it's monoclinic. And it has, I mean, it's one of these things which is ferroelectric and not ferroelectric. Or are you talking about a new compound you discovered?
Oh, this, okay. So that's I just simply take it from a database. So you're talking about this compound, right?
No.
Potassium iodate?
Potassium iodate is a perovskite. It's not that, I mean, it doesn't look like that.
Well,
I mean, I saw the structure. I mean, it's not.
So this is ICSD code. So I haven't looked at the papers, how they synthesize this compound, but
I think somebody needs to go through the database there.
Well, that's always a concern. A word of caution. These are results of high throughput application. I believe they're calculations, but if you really want to go to lab to synthesize, maybe it's better to first do a very careful, more accurate DFT calculations.
You can just look into the original papers.
Yeah, ICSD. So this is ICSD code.
I just wanted to go back to your band structure. You showed the band structure for a single domain.
Which band structure?
It was
electronic band structure?
Yeah, that's right.
Okay, the chart domain wall part. Okay.
Yes. So you showed it just with a single domain, and then you added in the domain wall.
Yes. So
it's become basically metallic. That's what it looks like.
Wow. Yes.
But my question is that band structure a 2D sort of band structure projected onto the domain wall, or is it?
Oh, this is just the whole.
It's the average of the slab.
Yeah, this is the whole Brillouin zone. But it's much better to look at the layer resolved density of states. So if you look at the bark-like region, it's still insulating. So, but here it's metallic. Well, at least you have quasi two-dimensional electron gap.
Yeah, because you write gamma, M, and K, so it's bulk, it's 3D.
Yeah.
Okay? So that means that the domain wall has made your whole slab metallic.
Well,
from the band structure, not from the density of states, from that band structure.
Right.